Recording for the midterm review. I'm going to go through these, show you my work, and if you have any questions, hopefully we have some time in class where we can go over some that you're confused by. The first one says the limit as x approaches infinity of this rational function. The first thing that I did when I saw this was I actually decided to distribute. All right, so distribute the numerator and the denominator. And when you do that, I actually wrote the 3 minus x as negative x plus 3. And when I distribute, I'm going to get two quadratic trinomials, one on the top. So negative 2x squared plus 7x minus 3 over x squared plus 2x minus 3. And if I plug in infinity for these, you'll notice that I'm going to get infinity over infinity, right? So kind of like we talked about with the lesson on L'Hopital's rule, what we can do is we can take the derivative of the numerator and the denominator and then try plugging in that value of infinity again. And so I'm going to do the derivative of negative 2x squared plus 7x minus 3 over the derivative of x squared plus 2x minus 3. So that's going to give me negative 4x plus 7 over 2x plus 2. All right, when I plug in infinity there, I'm going to get infinity over infinity again. So if you do another derivative of the numerator, that's going to be negative 4, derivative of the denominator is 2. So if you divide that, you'll find what your limit is equal to, which is negative 2, or answer choice B. All right, you could also just type this into Desmos, and you would find that the horizontal asymptote is at y equals negative 2 based on these leading coefficients here. All right, let's go to number 2. Number 2 is a basic integral problem. All right, so remember in the introduction we did to integrals, essentially we're just kind of going backwards. So we're trying to find a function that when I take the derivative, I get 1 over x squared. So the first thing I did was I rewrote this as x to the negative second power. So if I want to get x to the negative second power, I'm going to actually start with x to the negative first power, all right? Because when I subtract 1, I get x to the negative second power. But if I took the derivative of this, I would get negative 1 times x to the negative second power. But that's not what I want, right? I want positive x squared. So I actually need to make this a negative. And when I make that a negative, it's going to allow me to have positive x to the negative second power. So I'm looking for the answer choice that has the opposite of x to the negative first power plus c, which is letter D. Number 3, all right, I'm going to take the derivative here. Now this has a lot going on. This is the product rule and the power rule and the chain rule. So a lot going on here. The derivative of the first function, which is x minus 1, is just 1 times x squared plus 2 to the third power, plus the derivative of the second function using the power property, 3 times x squared plus 2 squared. Chain rule, derivative of x squared plus 2 is 2x, and then copy down the first function. All right, from here it just becomes algebra. So I wrote this as x squared plus 2 cubed plus 6x times x minus 1 times x squared plus 2 squared. Okay, and then I factored out x squared plus 2 squared, and that left me with x squared plus 2 plus 6x times x minus 1. If I clean up those inside parentheses, I'll get my answer here. That's x squared plus 2 plus 6x squared minus 6x. Combining like terms inside, I get 7x squared minus 6x plus 2, which if you look at your answer choices, the one that matches up with this is letter D. Okay, number 4. Number 4 is another integral problem. So again, we're kind of have to think going backwards here. I'm trying to find a function that when I take the derivative of it, I get the sine of 2x. Well, I know if I write cosine of 2x, then I'm going to get sine. But if I did the derivative of the cosine of 2x, I would get the opposite of sine of 2x times, right, chain rule here, times 2. But I don't want all of that stuff, right? I don't want this negative sign, and I don't want this 2. So I have to come up with ways to get rid of that. So if I put a negative in front of it, that will get rid of it, and also a 1/2. If I do the derivative of this, that negative 1/2 multiplied by this negative sign and that positive 2 would end up becoming just positive 1. All right, so that's my first piece. The next one is I'm trying to get cosine of 2x. So the sine of 2x would give me the cosine of 2x. But again, I'd have that 2 left over from the chain rule. So I have to put that 1/2 in front. So I'm looking for the addition of these two and then plus c, which would give me letter B. Now, number 5, if you plugged in 0 in number 5, you notice you're going to get 0 plus 0 over 0 minus 0, which is 0 over 0. So you're welcome to use L'Hopital's rule, but I actually think there's a simpler way to do this, even before you knew what L'Hopital's rule was. I would actually plug or factor out x squared first to get 5x squared plus 8 over x squared times 3x squared minus 16. Cross out your common factors and plug in 0. And after you do that, you'll get negative 8/16, which if you reduce is negative 1/2. Again, feel free to type this in, and you should have an idea when you look at Desmos on what it's going to be. Now, number 6. Number 6, I'm going to go to Desmos and type this in, this piecewise function for us. And I'll help us kind of understand kind of all these statements and just take a moment to talk about what they all mean. All right, so I'm going to type in my piecewise function, which is going to be for values that are less than 2, we have x squared minus 4 over x minus 2. And we have for values greater than 2, the same thing, x squared minus 4 over x minus 2. And then finally, for values that are equal to 2, or when it actually is equal to 2, it's just 1. All right, you might not see it yet, so let me zoom in for you. So we're fine as we approach 2 from the left. As we approach from the right, you'll notice the limit as x approaches 2 is 4. But when you go to do 2, you'll get an undefined value. All right, you'll get 2 comma undefined. So that's why they have this other piece in here, that 2 comma 1. And you'll notice that that should actually be an open circle at 2 comma 4. So that means this function is not continuous. And if the function is not continuous, then it is also not differentiable. So when I'm trying to answer this question, it does have a limit, because even though it's not defined, or excuse me, it's not continuous, it does have the same value as you approach x from the left and from the right of 2. So it does have a limit, but it's not continuous because it has that removable discontinuity, right, that open circle. And because it's not continuous, it cannot be differentiable. So the only answer here is actually Roman numeral number 1 for, or A for 1 only. Let's go to 7. Okay, so in 7, we have a particle that's moving along the x-axis, and it gives us the velocity function. And it's talking about the position of the particle at time t, and we're essentially being asked about the position. We had many conversations about this earlier on in the year. We have the position function, the velocity function, and the acceleration function. So we're here at velocity, and we actually have to back up to the position function. So the first thing I did was I wrote down trying to find the integral of 3t squared plus 6t, okay? So if I'm trying to find the integral of that, I'm going to start with t cubed, because if I take the derivative of t to the third power, that actually gives me 3t squared. And then I know I need t squared, but I don't have 2t in there, I have 6t. So that needs to be multiplied by that 3 to get me 6t, plus some constant c. And they're telling us that this right here, right, would be our position function based on the information. And they're telling us that when the position is 2, right, at time 0, I can plug in t is 0 and solve for that constant. So my constant is c is 2. So now I'm going to plug in, right, so copy down my position function now that I have all the pieces here. And we want to find the position when time is equal to 1. So I'm going to evaluate this position function when time is 1. All right, and doing that simple algebra gives me 1 plus 3 plus 2, which is 6. Number 8, finding the derivative of this f of x function and then evaluating it for the value pi over 9. So let's find d dx of the cosine of 3x. So that's going to be the derivative of cosine is negative sine of 3x, but then we have to take the chain rule, so times 3. So now, if this is my derivative of the f of x function, I want to plug in pi over 9. All right, when I do that, 3 times pi over 9 is the same as pi over 3. And if you don't know the sign of pi over 3, you can use a calculator. Use the formula chart from from the trig formula sheet. But essentially, I know that the pi over 3 is the same as 60 degrees, and the sine of 60 degrees is the square root of 3 over 2. So I'm looking for the answer choice that has this, which is E. Okay, number 9. Number 9 gives us the graph of the original function, and we're trying to find the graph of the derivative. And the way I do this, and there's a couple of ways to do it, but the way I like to do it is essentially when you're trying to find the graph of the derivative, I'm constantly looking at the slopes of tangent lines to this original curve. So you'll notice my slopes are positive until here where it's 0. Then now we're negative slopes until here where it's 0, and then back to having positive slopes. So I'm looking for the graph in A through E that has this, where I start with positive slopes, hit a 0 at about, I don't know, maybe negative 1 or 2. Then I'm to negative slopes to hitting a 0 about positive 2, and then back to positive slopes. So this first one is not going to work because it hits the x-axis. It does hit 2 places, but it doesn't. We're not going to cross at the origin, right? Again, they should cross at right here and right here, which is like x a little bit to the left and the right of the origin. B looks okay. Starting positive, crossing, then we're negative, then back to crossing and positive. C crosses too many times, doesn't cross 3 times. D doesn't start positive, right? These are actually negative y values. And this one, E never crosses. So B is actually going to be our answer for number 9. Okay, let's go to number 10. Now, number 10 says, if f of x equals this e to the 2 over x, then find the derivative. So I'm going to, if you need to use the derivative formula sheet, please use it. The derivative of e to the 2 over x power essentially is you copy this down, and then you multiply by the derivative of 2 over x. Well, 2 over x, right, can be written as 2 times x to the negative first power. So if I take the derivative of that, that's going to be negative 2x to the negative second power. So if I clean that up, I get e to the 2 over x. I'll throw the negative 2 in front over x squared. So I'm looking for this as my answer choice. And it looks like D is the only one that has x squared in the bottom. So 10 is D. All right, number 11. Number 11 says to find the derivative of f of the natural log of x. Well, I first need to find f of the natural log of x. So I'm going to plug in wherever I see x, the natural log of x. And then I need to find the derivative of that. So the derivative of the natural log of x squared plus 2 times the natural log of x. Now again, if you need to use the formula sheet, please. I'm going to use the power rule here, 2 times the natural log of x to the first power times the derivative of the natural log of x, which is actually 1 over x, plus 2 times the natural log of x. The derivative of the natural log of x again is 1 over x. Okay, so if I write that out, I have 2 natural log of x over x plus 2 over x. You have the same denominator, so you can add them together. And your answer choice that matches that would be A. Let's go to 12. Now, number 12 gives us this table of values for our function, and it actually gives us the second derivative. And the reason I put this in the review is because answer choices A and B are talking about where the function is increasing and decreasing, and that would be if you had the information about the first derivative values, okay? So whenever you see second derivatives, you're thinking about concave up or concave down. And when you're looking at the intervals here, from 0 to 2, we have a positive to a negative y value. So we're actually changing our concavity between 0 and 2. So the answer is E in terms of this second derivative information. Okay, 13. Wants us to find dy dx. This is called implicit differentiation. So I'm going to find the derivative of the sine of xy, which is cosine of xy. Chain rule. Using the product rule, I have 1 times y plus x times dy dx equals the derivative of x, which is 1. Okay, I'm going to move over some stuff with division. So I have y plus x times dy dx equals 1 over the cosine of xy. I'm going to subtract that y over. So it's going to be 1 over the cosine of xy minus y. I'm going to get a common denominator here before I move that x over finally to finish it. So the common denominator is cosine of xy, so that's not going to change. So it's 1 minus y times the cosine of xy all over the cosine of xy. So to finish it, all you do is move the x over with division, and it should look something like this. All right, so I'm looking for my answer choice that shows that, which looks like it's D. Let's go to 14. Okay, so in the xy plane, they tell us the line y, or the line x plus y equals k, or k is some number constant like 2 or negative 6. It's tangent to the graph of this parabola. What is the value of k? Now, you could type all this stuff into Desmos and use these answer choices as k, and you would find it. But I want to show you with some calculus and algebra of how to do it. So the first thing that I know is that if these are going to, if the line, which I'm going to write in slope-intercept form, y equals negative x plus k is going to be tangent to this graph, they need to actually equal to each other, right? So this, the first thing I know is that this and this are going to have to be, at some point, they're going to intersect. So I'm going to set them equal to each other, right? Set my y's equal to it and solve for k. You'll notice I won't be able to actually solve for k yet. So x squared plus 4x plus 1, all right? But the other thing I know is that if I take the derivative, right, of d dx of my parabola, that's equal to 2x plus 3. And if I were to plug in, right, the point value for x that's going to make this true, then I would get my slope of my tangent line. Well, what is the slope of my tangent line? The slope of the tangent line is equal to negative 1. So if this value for x is going to give me the slope of the tangent line, it has to be equal to negative 1. So now I can actually solve this for my value for x. So that's going to be x equals negative 2. And you'll notice now I'm ready to finish solving for k by plugging in negative 2. Again, I know it's pretty complicated. It's also been since one of the first lessons that we did on calculus back in September. It's going to be 4 minus 8 plus 1. So 4 minus 8 is negative 4. Negative 4 plus 1 is negative 3. All right, but again, you can use Desmos to confirm if you'd like. Okay, 15. We have a function, and it says the second derivative is given by this, and what are the x-coordinates of the points of inflection of the graph of our original function f. So this is saying whenever you change concavity, right, going from concave up to concave down to concave up, you have a point of inflection. So in this case, if I find my critical points, all right, so set this second derivative equal to 0, I have x squared times x minus 3 times x minus 6, my critical points are 0, 3, and 6. So if I break down my interval into negative infinity to 0, 0 to 3, 3 to 6, and 6 to infinity, and do a little sign analysis, I can figure out where my function is concave up or down, and ultimately then find my points of inflection. So sine of the second derivative. All right, so I'm going to plug in negative 1. All right, negative 1 squared is positive. Then I have a negative and a negative. That's also positive, so that's going to be positive. So concave up. I'm going to plug in positive 1. So I get a negative, and that's another negative. But then that's a positive times another positive. So that's positive. Plug in 4. You can plug in 5, whatever you want. Plug in 4, I get a positive. Then times a negative is a negative times a positive is a negative. So that's concave down. And finally, if I plug in 7, everything is positive. So back to concave up. So when I switch from concave up to down and then concave down to up, I have points of inflection. So that's going to be at 3 and at 6. All right, so 3 and 6, so D. Okay, 16. All right, on this one, we're looking at the graph of the particle's position. All right, and we have horizontal tangent lines at t equals 1 and t equals 5. All right, and a point of inflection at 2. For what values of t is the velocity of the particle increasing? So actually, if this is the position function, if I take my derivatives, right, and look at here, we're actually starting out super steep negative, but then we're slowly getting, let me show you a little difference here. You're slowly getting less steep negative. So it's actually increasing right at the beginning. And we're still increasing until we get to our point of inflection at 2. And that's when we're actually, our velocity is decreasing. We're getting less positive steepness. All right, so we actually are switching to concave down. So that's why this is only increasing between 0 and 2. Okay, 17. All right, so 17 says the function is twice differentiable and gives us all this information. This is a linear approximation. Here's the formula that we used in the past and you used on the chapter 4 test. So I'm trying to find the linear approximation of 1.9. So I'm going to do f of 2 plus f prime of 2 times 1.9 minus 2. All right, so that's going to give me f of 2 is 1, f prime of 2 is 4, 1.9 minus 2 is negative 0.1. Doing my algebra gives me 1 minus 0.4, which is 0.6, or B. 18, this is my personal favorite, giant amount of space. There's going to be a lot of work here. So we're trying to figure out with this piecewise function, the values for C and D that are going to make this differentiable. We know it has to be continuous for it to be differentiable. So the first thing I do is I set Cx plus D equal to x squared minus Cx, and that is going to occur when x is 2 for this to be continuous. So I'm going to plug in 2 for x. All right, clean it up a little bit. Get 2c plus d equals 4 minus 2c. Solve for d, and you get 4 minus 4c. Okay? Now, in order for this to be differentiable, as we approach the limit of x approaches 2 from the left, it has to be the same as the limit as x approaches 2 from the right. So this is where I'm going to use the function on the left, which is cx plus d, minus, when I plug in 2 for x, you're going to plug in c times 2 plus d over x minus 2. So if I make this a little nicer, that's minus 2c minus d. You'll notice my d's are going to cross out, and I'm left with just cx minus 2c. I'm going to factor out my common factor c. You notice my x minus 2's will cross out, so the limit as x approaches 2 from the left of this is just going to be equal to c. All right, now I'm going to do the same thing, but on the right-hand side. All right, so from the right, I'm going to be using x squared minus cx minus the same thing I used before, which was 2c plus d over x minus 2. All right, so I'm going to distribute, get minus 2c minus d. All right, but now what you'll notice is that I'm not going to be able to cross out anything, so I'm going to plug in where it says d, right? I'm going to plug in this for d right there. So I'm going to plug in 4 minus 4c, and I'm just going to ignore my denominator for a little bit until I'm ready to bring it back. So x squared minus cx minus 2c minus 4 minus 4c. Confirm I got that? Yep. So now I'm going to distribute. So minus 4 plus 4c. Organize some things so I can do some factoring. So x squared minus 4, I'm going to organize first. Minus cx, negative 2c plus 4c is 2c. I'll bring my denominator back in now. Factor by grouping. So that's x minus 2, x plus 2, minus c times x minus 2. Okay, all over x minus 2. Your common factor is x minus 2, and you put together x plus 2 minus c. You'll see what crosses out. So I have the limit as x approaches 2 from the right is just x plus 2 minus c. Plug in 2, you get 2 plus 2 minus c, so that's 4 minus c. Remember, those pieces have to be the same. All right, we found c for the one on the left, 4 minus c on the one on the right. So c is equal to 4 minus c, or 2c equals 4, so c is 2. Using my d equals 4 minus 4c, I find that d is equal to negative 4. All right, so those are my values for c and d. It wants me to add them for some random reason. So 2 plus negative 4 is negative 2. That is an incredible problem. Amazing. That's 18. Let's go to 19. All right, we have a differentiable function. All right, and it wants us to find the value of g prime of 3, and g is the inverse of the f of x function. So using the formula sheet, g prime of 3 is the same as 1 over f prime of g of 3. Okay, it gives us this information. G of 3, it doesn't say we have it, but if it's the inverse, do you see how this says f of 6 equals 3? So then g of 3 must be equal to 6, right? Because inverse is you switch the x and the y's. So it's 1 over f prime of 6. F prime of 6 is negative 2, so the answer is negative 1/2. Let's go to 20. All right, on this one, it wants us to find where the intervals where the original function is increasing, right? When I look at the graph of the derivative, as long as the values for y are positive, that's where it's increasing. For the values of y where it's negative, that's where the function is decreasing. So in this case, I'm positive from negative 2, right? Negative 2 all the way to positive 3. So that's going to be where my original function is increasing, which is b. 21. We want to see which of these statements is true. The limit as x approaches 2 from the left. As you approach 2 from the left, you're approaching a y value here, so that does exist. As you approach 2 from the right, you're approaching this y value, which does exist. So those two exist, but do you see how they're approaching different values? Since you're approaching different y values from the left and from the right, the limit as x approaches 2 does not exist. So only 1 and 2 are going to work here. So C. Okay, 22. All right, they're giving us the velocity function. We want to find the acceleration. So kind of like we talked about before, you have position, then velocity, then acceleration. So we need to find the derivative of this velocity function, 7 minus 1.01 to the negative t squared. All right, so derivative of 7 is just gone. So I have that negative sign. When you have the derivative of this exponential function, again, you can refer to the formula sheet if you need to, but what you do is you write down the function again. Okay, then you find the derivative of the exponent, and the derivative of the exponent is going to be negative 2t. And then you write down the natural log of that base, which is 1.01. All right, you can clean this up if you want, but this is essentially the acceleration, and we want to find when time is 3. So I'm just going to plug in wherever I see t, I'm going to plug in 3. Please move to Desmos when you're ready. All right, because that's where I'm going to type this in to find the answer. You could also just use, your cell phone would do it too. All right, so I'm going to type in negative 1.01 to the negative 9th power times negative 6 times the natural log of 1.01. So my answer is 0.055. Which is B. All right, 23. All right, in 23, we have the graph of the derivative. We want to find at which of the following values of x does f have a relative maximum. So relative maximum for your original function would be going increasing to decreasing. So essentially, I'm looking for where does the derivative go from positive to a negative. So positive to a negative would be right, I'll kind of highlight it for you as I'm looking, would be positive to a negative. So right there at x equals 4 is where you're moving from positive to a negative. So we'd have a relative maximum right there. So we're increasing, and then we're going to be decreasing. So C, x equals 4. 24, almost done. 2 more to go. 24 gives us all this information about a velocity function, and we're trying to figure out what could be the graph of the position function. Again, that's backing up. So all this information in the table is about the first derivative of that position function. So when I'm looking at this, I notice that I have a negative to start. So I'm actually decreasing to start, but then I'm increasing and then finally decreasing again. So when I look at my original, I should see originally decreasing first, which the only one that decreases to start is actually C, and then finally decreasing right here, right at the end. Okay, so that's why 24 is C. The last one, 25. All right, this is one of those related rate problems. You have the surface area equals 4 pi r squared. We're going to differentiate with respect to time. So you get 4 pi times 2r times dr dt. We're trying to find the change in the rate of change of the surface area of the sphere when our radius is 3. And it says the radius is changing at a rate of 2 centimeters per second, but it says decreasing. So make sure you plug in that negative. All right, so that's going to be 4 times 2 is 8, times 3 is 24, times 2 is negative 48 pi is our answer, or letter C. All right, and that's it, guys. I know I went pretty quickly on a lot of these, but hopefully you have a chance to watch it. And please ask questions in class if you have any other issues. Good luck.